13.2 Measuring Distance in Space. The universe is insanely large and getting larger every second with expansion. It's estimated to contain 100 billion galaxies and a 1 with 22 zeros after it number of stars, or 1 times 10 to 22. Huge, huge number, a number you could not count to in your lifetime. Well, in order to deal with such big numbers of stars and galaxies and the vast size of the universe, we need bigger units. When we measure distance here on Earth, we often go in centimeters, meters, kilometers. Well, here we need a different scale. So we have something called 1 light year. We like to measure things in light years. That is not a unit of time. That is a unit of distance. It is how far light travels in 1 year. You should know from grade 8 that light travels at 300,000 kilometers every second. And that translates into 9.5 trillion kilometers per year. So if you went 1 light year, you would have traveled 9.5 times 10 to the 12th kilometers. A whopping number. Now we have something called an astronomical unit. And that is simply defined as the distance, approximate distance, between the Earth and the Sun. There's something called the baseline method, using something called parallax. And you see a picture of a tree and a person, and what it involves is a bit of geometry. And as you move and take different angles, you can work out how far you are from that tree. And so the tree would represent, say, the star, and you would represent the Earth, and you're trying to figure out how far it is. We're not going to make you do the math of it. This is just to give you sort of a qualitative view of how to tackle these things. Well, let's look at the Earth's orbit around the Sun. It is not round, it's elliptical, and we have summer and we have winter. But this distance is around 150 million kilometers here, and around 150 million kilometers on this side. So in other words, our baseline is 300 million kilometers from the Sun, or the Earth's position relative to the Sun in summer, and the Earth's position relative to the Sun in winter. So using that baseline, and using something called parallax, we can calculate the distance to stars that are 200 light years away or less. Beyond that, our angles get so small, we will not have much precision in there at all. The last thing on this page is something called absolute magnitude and apparent magnitude. Now here on Earth, when we look at a star, some stars will appear brighter than others. And some stars might have the same brightness, or actual brightness, or absolute magnitude is what it's called. But in fact, one will appear brighter than the other because the one that appears brighter is closer to us. And so astronomers have to account for this. They have to account for difference in brightness of stars, and they have to look at how much that's affected by the distance away from us here on Earth they are. So let's look at these definitions. Absolute magnitude, the actual amount of light that a star gives off. That's what we'd like to know. Apparent magnitude is what we see here on Earth. So astronomers are having to take that apparent magnitude, get information about the star, and then calculate the absolute magnitude. You will get some questions on this topic in 13.2, but really we're going to shy away from the math part of doing calculations for distance to far off objects. So that's it for this video.